Hi, everyone. My name is Abe, or Abraham, and I'm here to basically guide you through some of the interactive portion here. So you learned a little bit about FireSim, a little bit of what its original goals were, the data center style simulation where you're running 1024 nodes all at the same time, all cycle accurately. Now let's actually have you simulate your own design, boot Linux, and actually run interesting workloads. So first, we're going to talk a little bit about what you did this morning and kind of the thing that you prefetched, which was building your own hardware design for FireSim, your own bit stream. So what will we cover? So here we're going to talk a little bit about the compiler itself. So when we talk about FireSim ingesting Fertile and then emitting both a bit stream as well as a C++ driver, we're going to talk a little bit about how that's done. That's called Golden Gate. And we're going to actually invoke it on a sample example RTL design. And then we're going to actually look at the outputs. So we're going to look at what FireSim is doing underneath the hood so that it can actually run something on the FPGA, but also interact with it on the host. And then we're also going to talk about the manager itself. So FireSim basically uses this command to basically manage the simulation, both build things like you did this morning, as well as run them as well. So we're going to talk a little bit about the configuration system, about how do you actually make this command do what you want it to do. And then finally, what you did this morning, we're going to talk a little bit about building bit streams. So where is FireSim Chipyard? So you all have access to your EC2 instances. Hopefully you guys can continue to stay inside of that EC2 instance and SSH back in. And basically, since FireSim is another form of a simulator, it lives where all the simulators are. So here, this was kind of the folder of where FireSim is. It's going to be in Chipyard Afternoon, Sims FireSim. And we've actually conveniently exported it as $FDIR so that you have to type less. So for future reference, you're going to see this inside of the commands that you're going to run as FDIR. But this is where FireSim lives. So first things first, for the interactive session, go ahead and create a new TMUX session, call it afternoon or whatever you want, as a particular name that you can reference it as. So go ahead and make that. And then go ahead and go to the FireSim directory and type ls. So we just want to look a little bit about what exists in the area. So I'll give people a couple seconds so that they can do this. And of course, if you have any questions with any of the interactive stuff or any questions in general, feel free to raise your hand. One of us will run around and help you out and or answer the question. OK, so hopefully that wasn't too bad so far. Now let's actually look at what the directory structure is for FireSim. So one of the first things you might see is this sim directory. And this sim directory is basically where the compiler lives for FireSim. So this is what's taking that Fertile that's emitted from something like Chipyard, doing a bunch of stuff to it, and then emitting a Verilog that's going to be passed to something like Vivado, and also building C++ drivers that are interacting with it on the host. So like it says here, you're going to have things like FireSim models, the compiler itself, the make-based build system to invoke Golden Gate, and much, much more. You should also see another folder that's called deploy. So deploy is basically where the manager lives. So that command line Python top level that's called FireSim. That's where it lives, inside of deploy. And so not only do you call the FireSim command here, but this is where you actually store software for FireSim to run later on in simulations. So you'll have workload definitions, and I'll go into what exactly that means. What's a workload in terms of FireSim? And then, of course, for those that are interested in hacking up your own FPGA and implementing it in FireSim, there's this platforms directory, which has the implementation for AWS F1 FPGAs, and it also has implementations for Vitis U250 FPGAs, which are supported locally. And then finally, we have software directory, which is basically another tool that's going to build our Linux distributions, build our bare metal tests, and we'll go into this a little bit later. So that's the software folder. Cool. So let's actually dive a little bit more into the compiler and see what the compiler is doing. This is called Golden Gate. So back to interactive slide here. So go ahead and go into the sim directory. you guys will probably also, you'll already be inside of the Efter area, but go ahead and enter sim and then type make all caps design equals FireSim. So what we're doing here is we're invoking the make base flow to build an example design, kind of the default FireSim design. So we're running Golden Gate. So I'll give a couple seconds for people to type that out. As a reminder, the slides are up on the website. So if I move a little bit too fast, you guys can at least look at the slides on the website and follow along. Yes.
Module FireSim.
Can you make sure it's capital F, capital S? Yeah, no problem. Yes, so with any of our tools, we are very susceptible to any typos. Case sensitive commands here. So it's all caps design and then capital F and S in FireSim. Hopefully it should just work instantly because we pre-cache things for you. But this would actually invoke the Golden Gate compiler. So let's actually go into an analogy and see what was actually run when we type this make command. So Golden Gate is like Verilator, but for FPGA accelerated simulation. We talked a little bit about this in the prior presentation. And Verilator, excuse me, generates C++ sources for your RTL. So it's going to compile it and run it on a CPU host. Golden Gate is similar, but it's doing two things. It's compiling C++ sources, and it's also generating Verilog that's going to be passed to something like Vivado so that these two things can talk to each other, the FPGA bit stream that's running on the FPGA, and then the host driver. So compile and run on a hybrid CPU FPGA host. So the Golden Gate compiler is basically just a way that you take your target fertile and some extra metadata and then dump out a bunch of extra information. So it has things like the fertile and annotations from a Chipyard generator. Doesn't necessarily have to be Chipyard, but for the most part, it is Chipyard. So fertile is the design, the target design that you're intending, the 28 boom core example, for example, and then annotations, specific pieces of metadata from Chipyard indicating what the design is. A compiler configuration, right? So am I targeting an F1 FPGA that has a certain amount of resources, certain amount of BRAMs, whatever the case is, or a Vitis-based FPGA, a U250. And then it produces sources that are deterministic, so you're not going to get any sort of variance. And then it allows you to have software models running in tandem with the bit stream. Yes?
Where do Verilog black box models fit into that flow?
Yes. So one of the things that we lighted here is that basically the inputs here is fertile annotations from a Chipyard generator, but it also includes the black boxes that come from Chipyard as well. So the fertile itself is basically going to have the wrapper to the black box module, and then the annotation is going to say, here's the path to a Verilog file. When that gets passed to Golden Gate compiler, it's basically going to go ahead and find that Verilog file or system Verilog file, take it, copy it into like a build directory that the compiler is going to work on, and then it's going to emit all of the Verilog sources that it compiled from the fertile as well as your black box module with some extra like queues and clock gating around it. So maybe this slide should be updated in the future, but this is fertile anodes. That includes your custom Verilog chisel, whatever the case is. Cool. And of course, since we're working with FPGAs, the compiler is actually made to be more area optimized for different types of FPGAs. And so we have many different features to basically allow you to make trade-offs in terms of time for area. So if you're willing to spend a little bit more time, you can actually reduce the size of things that are running on FPGA. And I'll have an example of that in a second here. So what we ended up doing was we ended up interacting with this compiler with make. So we called that make command. And that make command basically involves three different things. We only talked about one or only added one in that interactive section. And these three variables are called the tuple in FireSim parlance. And it's basically the design. That's what you ended up doing. The default design is going to be the model in Chipyard, in this case, the FireSim model of the design. The target config, which is basically analogous to the config that you were modifying this morning, the 28 core boom config, the XYZ knock config, whatever the case is. It's basically your target config, what you're actually simulating on the system. and then the platform config. And this is basically all the options that you pass to Golden Gate, right? So any sort of FPGA optimizations, or am I running on an F1 FPGA or running on a Vitis FPGA, things like that. So now let's actually look at the output of what we've seen so far. So go ahead and go into the generated source directory inside of SIM. So you may be already in part of SIM, but this is just kind of a full path here. So go ahead and go into generated source F1 and then type ls to look at some of the output. Here you should see a bunch of directories for all the builds that we've kind of pre-cached for you so far, because we ran the compiler a couple of times. And just go ahead and enter any of the directories. It doesn't really matter which. CD, use tab complete to enter a particular directory, and then go ahead and ls. Cool. So while you do that, I'll talk a little bit about some of the files that you might see. So you'll see a couple of things. First is a .fir file and a .ano.json file. And this is basically your target RTL and annotations. It will have the wrappers to any sort of black box Verilog as well. In this case, the default design doesn't have any black box Verilog. So it's mainly just fertile and ano.json. But this is basically what you're passing from Chipyard to FireSim, so it knows what it's going to be executing on. You have a really large system Verilog file. If you open it up, it's going to take a while to load in something like Vim and less. But basically, this is what the compiler created. This is that Verilog that's going to be passed to Vivado or to the synthesis tool to actually make into a bitstream. FireSim generated SV. And then you should see generated.const. This is basically the simulator's memory map. So if you remember, you have a part that's running on the FPGA in the simulation, as well as something that's running on that C++ host that's interacting with the FPGA. This is basically the interface between the two so that you can interact back and forth with the simulation that's running on the FPGA. So feel free to enter any of these, look around, see what exists. They're kind of big monolithic files. Next, we'll talk a little bit about the manager, which is the FireSim command. So in this case, we're going to talk a little bit about its configuration and what does it actually do. So some background terminology here. So this is basically the picture that we refer to in the AWS side that shows both build farms and run farms. And I'll talk about what those are exactly. When you are running a simulation, you have an FPGA bitstream. We're going to call that an AGFI, an Amazon generated FPGA image. It's a little bit of a big acronym here. But basically, that's basically the bitstream that's going to be running on a particular FPGA. So when you're using the FireSim command line, you first need to just generally run a particular file called the source me that basically puts the FireSim command on your path, right? I need to be able to invoke it from anywhere, and it will always run from the deployed directory, which is what you saw earlier. So we already did this for you, and we already ran the following command, which initializes the manager for a particular platform, in this case, for F1. So we ran this FireSim manager in it for you already, and then you ran it earlier today if you needed to build an FPGA bitstream. So we already did this, so this is why it's not marked as interactive. So let's go ahead and go into deploy and look around at deploy, and we're going to start looking at some of the configuration files for this FireSim command, this FireSim command line. So what you should see is that when you ls inside of the fdir/deploy directory, you should see 4 files that exist: config build recipes, HWDB, and config runtime.yaml. These are basically the inputs to that Python API, that Python FireSim program that basically configures how you're going to do simulations, what you're going to run, what you're going to build. So we'll dive a little bit into each of these in particular. So the first one is the build files here. So config build.yaml and build recipes.yaml. So if you look at, let's first look at config build recipes.yaml. So you can go ahead and open it up. and look at a particular entry here. The entry looks maybe slightly a little bit different in more modern versions of FireSim, but the point still stands here. So it consists of a couple components that specify what you're actually building. What's the simulation that you're building, including the bitstream. So it consists of things like a label. So that's a unique name that you're going to give it. Call it my cool design that I'm planning to get a paper on, right? You put that right there. The tuple that I mentioned before, right? So it's indicating, you know, what I'm passing to the compiler, what's the actual design that I'm running. So here it's a little bit cut off, but you would see like Chipyard, rocket chip, or Chipyard, my knock config, like somewhere down here on the end, and then the actual design indicating the top level. It's a FireSim simulation. It also has platform-specific information. So for example, this recipe is made for F1. So it has something that's called a bit builder recipe, which I'll talk a little bit more about in the local FPGA section, but it basically specifies I'm going to use the F1 version of an FPGA bitstream process to build it. And there's some other fields here that also do platform-specific items as well, indicating timing, like a particular FPGA frequency that you want to target, for example. So now we've defined what the build recipe is. We've specified this is some rocket quad core with a NIC. Now we need to actually build it. So this is what you did earlier. So if we look at the other file, which is config build.yaml, you should see something that looks like this. So you'll see something at the top, that's the build farm, which is basically the build host configuration section, basically indicating that I'm running on AWS, and it has a bunch of AWS default parameters indicating what's the name of instances that I'm launching, what's the instance type, things of that sort. And then it specifies what builds do I want to run. So in this case, I have a list of builds that reference the recipes that we mentioned before in that other file to build. Then you have AGFIs to share. So in AWS's case, you have a way that you can actually share these bit streams with others on the cloud. That's what this section is for. You basically list it here, and then you can actually click a button or type a command more so, and it will automatically share the bit stream to other people on AWS so that if you're working in a group with other people, they can download that bitstream build and use it. So this is basically the quick overview of the build files. Now, running builds. So you're going to see something after we've configured what we want to build, we actually need to click a button. So this was the command that you ran earlier in the day to kind of prefetch a bitstream build, FireSim build bitstream. You would type this command. It's going to read those two files. It's going to read what the recipe is, what your simulator is, what your target is, compilation options for Golden Gate, and actually run it. Run that particular list of things. So it does a lot of things in parallel. So it launches a build instance. So in the case of AWS, you are here on what's called the manager instance. It's going to spawn a build instance corresponding to a particular build or a particular target. It's going to launch it. It's going to generate the RTL and invoke the compiler. And then it's going to copy all of the extra things that you need for Vivado to run or whatever your synthesis tool is to run. It's going to copy it to that machine, invoke the actual synthesis build. And then once it's done, it's going to copy it back to your manager instance. And then, of course, tear down the machine. So in this case, if you ran a build, you would see something like FDIR deploy results build, and it would have all the collateral that was done by Vivado for the bitstream build present there. And in your case, when you signed up for an email, hopefully when you typed in FireSim Manager in it, you would have gotten an email by now indicating, hey, your AGFI has been created with something that looks like this. So this is basically the output of what the FireSim build bitstream shows. And as I mentioned, terminates the build instance. So it does this in parallel for multiple different builds that you're trying to run in parallel. So if you need to build one simulation that has a rocket core, an in-order core, another with an out-of-order core, with some different tweaks, you can do those all in parallel with the cloud by scaling out. So what did we actually see in that email? That's basically what we call a hardware DB entry. And so a hardware DB entry kind of similar to before, has the name of the recipe that it corresponds to. So remember, what does it actually specify? What do you want to build in simulation? What's the actual output? It has a particular FPGA image associated with it. In the case of AWS, they have AGFI strings. So it's this unique identifier for the bit stream that lives in the cloud. And then other miscellaneous hooks indicating software models and runtime arguments. For the sake of this conversation, we probably won't go too much into detail on the hooks to change, but we have plenty of documentation online about what exactly those do, but those are mainly for power users. I saw a hand over there for questions. Yes. So the question was, how do I actually specify the config? So that's in the build recipe. So if I go kind of back here, inside of this file, config build recipes, you have basically kind of the top level module that you want to do, and then you have your target config. So you would have Chipyard, my really cool paper config. Yay, there, whatever the case is. And then you specify that unique name here, you click build bitstream, and then it ships out. Okay. So we've learned a little bit about the build process here, and we've learned about what gets output. Now, so in summary, we actually did all of these steps already. So notice how there wasn't like too much interactive portion here. That's because we ran it earlier, because FPGA bit streams take a while to build. So don't worry if you didn't catch too much here. We detail this in excruciating depth on the website itself. And we've actually learned a little bit about how do we actually configure the FireSim command to do what we want it to do. So in the next part of the talk, we're going to run the build stream that we built and actually boot Linux on it and run some interesting workloads.